Hello and welcome to a discussion about the FLAIR network. This presentation will be given in multiple sections, and you're welcome to watch each video in sequence. Hello again, welcome to part 2 of the FLAIR presentation. For this section, we'll be concerned with products from FLAIR, what we produce and how we produce them, and give a little tutorial in terms of our calibration and fundamentals. So with that being said, let's jump right in. So the FLAIR portal is how you access all this information. It's kind of set up like a calendar. You can see here a number of looks have been taken on the calendar. This is all a historical look. But basically, I would choose a day or a date range that I might want to get a calibration. I would choose a satellite and a FLAIR station that I want to use for calibration. And I'd basically put all this information in, and it's super easy to do, takes about 5 minutes, and then a calibration is set. There is another video explaining how the FLAIR portal works, and I encourage you to watch that if you're interested in seeing how easy this is to do. We call this calibration as a service. So this is moving away from the hardware and having to purchase hardware, but actually the hardware is there. Labsware maintains the hardware. We do the calibration and the hard work of the system. What you access is the availability of the system, and you access it when you need it and the way you want to use it. And this can be used not just for your satellites, it can be used for any satellite. Let's say I'm a satellite data provider, small satellite data provider, but I want to harmonize with Sentinel or Landsat. I can schedule looks with Landsat or Sentinel. I can schedule looks with other competitors' satellites as well. Now, the image, you have to go get the image. We don't take the image, you take the image, so we don't actually touch that. Unless you give it to us. So the FLAIR products are really about calibration and the calibration packages. The image is yours. So when you've conjured up an image, there's usually two things that people want to do. One is they want to take a look, which would give you some degree of calibration information, either spatial or radiometric, or they might want us to actually do some more analysis for them. And that would require us getting back some imagery from you. So let's first go over the lower column here, which is the look. So in the look, we basically either do a spatial look, which provides the point spread function and information, the information about the mirrors and other ground control points, GPS locations, etc., to allow you to do a point spread function analysis. That's a look S for spatial, or there's a look R for radiometric. So that combines, it gives you the spatial information in the look R. So a spatial look is inherent in a radiometric look. You need both radiometric and spatial. But then on top of that, we're deploying the radiometric tower and giving you the spectral information that you need there. So we have a look S for spatial and a look R for radiometric, which includes the spatial and radiometric. Then, if you've done that and you don't want to do the analysis, or perhaps you want a third-party traceable verification of the information that you've gotten from your analysis group, then you can send the images to us. Here we see a bunch of point spread functions that the customer uploaded, and then we're able to create a traceable point spread function and send that back. That's what we call an eval. And so there would be an eval S for spatial or an eval R for radiometric. And in the case of the radiometric, now they're not only sending us the general panchromatic image, perhaps, or the band image, if it's just they're interested in this spatial and a band, but they're sending us actually the band specific information. And then we're deriving more specific information about the band, gain coefficients, or the spatial response of that band, or spatial, maybe even spatial misregistration. So these eval products are done after you've uploaded the image back to us. It's a second paid service on top of the look. The looks are the primary service. The evals are where we can provide a third-party traceable analysis for you very quickly by just uploading your images back to us. So this is another look at that. So we have the look S, which provides the node data, the mirror configuration, and the quality of the look, meaning how good was the atmosphere that day. Look R is a radiometric look, which gives you additional radiometric information, derived information. And then if you upload the images to us, we can give you, we can complete the circle and give you the rest of the information associated with the spatial or radiometric, depending on which eval you've ordered. So let's just look at what an eval S is. So this is 3 eval S's taken on Sentinel-2B. So we have July 1st, July 11th, and then July 31st. Now, Sentinel is a very high quality telescope, so we were able to get really good point spread functions out of a single image. And that's uncommon. That's a world-class satellite. Smaller satellites, generally we need more images to be able to develop a point spread function, somewhere between 6 to 15. In this particular case, we're able to use those 3 images together. You see there's not a whole lot of variance image to image here because, again, it is a very high quality satellite. But when we put them all together, now we're able to put together statistics and create an oversampled point spread function, which gives you a lot more accuracy and a lot more error in terms of the error function, and much higher confidence in the point spread function, and which can be used then for MTF analysis and so forth. So that's it depends on how many images you give us, the quality of the image the quality analysis we give back. So a look-R, let's just look at that, and let's look at look-R's radiometric validation and atmospheric extraction, just to talk about that a little bit. We use 2 methodologies in the flare stations. We use a Langley-informed calibration, which is actually staring at the sun through the atmosphere or the better course of a day. This is a well-established methodology for many radiometric characterizations, including AirNet. And then you know the top of atmosphere from the sun because you got that from an instrument like the TSIS-1 above the atmosphere. And then you're able to correlate that top of atmosphere against the atmospheric extraction, and using specific what I call Langley peaks. These are known kind of stable or common reference points in the atmospheric spectra. And then you're able to derive a calibration curve off of those peaks. That in turn enables you to look at some upwelling and downwelling atmospheric extraction. We also use MODTRAN to augment the Langley plot. And then we provide the ground measurement, which is derived out of the upwelling and downwelling and the top of atmosphere all combined. Now, for a Langley plot, you need a really good days to do that. You can't do them every day. You have to have a perfectly clear sky. You've got to have a long period of perfectly clear sky, and so you only get a few Langley days a year. But once you have them, the instruments are pretty stable, so they're good. But but to augment that, we put in a second calibration device into the flare systems, and that is in the radiometric tower. When the instrument is stowed, we actually have an integrating sphere in there, and that integrating sphere is calibrated traceable to NIST. So this one, the Langley, is traceable to the TSIS-1 at the top of atmosphere on the International Space Station. The second system on the integrating sphere is directly traceable to NIST. So we have 2 completely independent calibration traceabilities, which provides a robust backdrop. These 2 things should absolutely match each other within their uncertainty. But the sphere allows us to calibrate at will. So if we're concerned about the stability of our instrument, we can calibrate before every look if we want to. And then additionally, you see there's atmospheric peaks here, and that's an artifact of the Langley method. Is you're going to have the atmosphere, you're going to have atmospheric peaks. You'll see this in the next graph. With the sphere, you don't. You have a nice continuous atmospheric radiant spectra, and that provides the ability to perhaps fill in some of these spaces where you're going to see some atmospheric variance. So let's take a look at an actual radiometric capture for Sentinel-2A. So here is a graph presented in a similar fashion to the RadCalNet. So this is smooth data. The blue line is the absolute measurement. The orange lines are the upper and lower bounds of uncertainty for that given measurement. But the Full spectral resolution we can also provide, because on our radiometric tower we actually have a spectrometer from the 350 to 1,000 nanometer range. So we can provide you not only the unsmooth data, just the raw data. And that's typically what we do, because the smoothing functions are really a question of taste and preference. This is the way RadCal does it, so we can present that. But a lot of customers just want the raw data so they can do their own extraction on this. And so this is the 1 nanometer data for the at-sensor spectral intensity at the top of atmosphere, at the sensor, or at the aperture of the sensor. And then below that, we have the black line, which is the actual 1 sigma uncertainty in 1 nanometer increments. And you can see that there's a little spurious thing here, which is due to the spectrometer on this particular capture. But wavelength by wavelength, we're at about 3.5% absolute, K equals 1. But then when you start getting out into the atmospheric bands, this is where the sphere versus the Langley could be really helpful, because the peaks that you see here are because of the atmospheric variations along the Langley calibration. The sphere doesn't have that, so we have a dual baseline that can potentially smooth that out. There's more information in some of our papers on that. So that was a look-R. This is what a look-R would give you. This is an eval-R, so if you upload the images and you've told us what the RSRs are for the bands of interest on each one of these, so this is band 2, 3, 4, 5, 6, 8 for Sentinel-2A, we can give you a radiometric coefficient for each band based on the RSRs that you sent to us. So this is a traceable third-party evaluation of that image radiometrically. If you have any more questions, contact Labsphere Incorporated at 603-927-4266, or email me, cdurrell@labsphere.com, Chris Durrell, and we'll be happy to answer any questions you might have.